It's 2 hours. Yeah, 2 hours.
Maybe I'll
Alrighty, so I guess we can just begin. Thank you everyone for coming IRL and everyone who's watching online. We all good? Yeah. Okay, so yeah, here's just a QR code just for attendance, right? Would be pretty cool if you know everyone scan that.
Wait, why is that one?
Yeah, it's just frozen. Okay. We've got the Hollywood Under the Harbor cruise coming up as well. So just a little promo beforehand. If you haven't already got tickets and you still can, we highly recommend. It'll be a lot of fun coming to the Hollywood Under the Harbor cruise. And yeah, I guess let's just get into it. Okay, so the Maple workshop for 1B, right, 2025. Pretty much just an overview of how this is going to go. We've split it up. So first, we're going to talk about multivariable operations and just functions of more than 2 or more variables. Then we'll move on to just like stuff that we're going to need for 1B calculus and 1B lineage. And then I'll pass it over, and then we'll talk a lot about 3D geometry and programming in Maple. Cool, so without further ado, let's just get into functions of 2 or more variables. But in order to do that, we first just a brief recap from 1A. In Maple, it registers 2 types of real equations, and those are expressions and functions. They're exactly what their name suggests. So an expression is just some expression, some relationship between variables. Meanwhile, a function is a mapping between an input set to an output. And so they work slightly differently in Maple, and so we're going to need to be aware of how they work using like a couple of different commands, but functionally they can both achieve pretty much the same thing. So for example, if I wanted to define a expression, just say E, right, I'd use this colon equal sign, and then I'll just start writing whatever I want to write. So in the example, we have x squared times y minus x. And you'll see that just defines an expression. So it's just a relationship between x and y, and we call that relation E. Meanwhile, I can do the same thing, but define it as a function. So let's do f for function. So what we say is it takes in an input, x, y, and then it outputs, using this arrow, the output that we want it to. So in this case, it'd be x squared times y minus x. And so yeah, you can see here, this arrow just means it's like a mapping between the input and the output that we desire. And so with expressions and functions, we're going to use slightly different commands. And so it's really important to understand the difference. For example, with functional notation, it's kind of intuitive. If I want to just plug in 4,2, for example, I can just do f of 4,2, and it gives me 28, as we expect. But if I were to try the same thing for our expression, e42, it kind of like panics a little bit. And that's because Maple isn't understanding it as like a relationship between inputs and outputs. It's giving me this random relationship, and you've given it like some random numbers, and it doesn't know what to do with it. And so for an expression, we want to use the subs command. So it's subs, and we sub whatever we want to do. So for example, we want to sub x equals 4 and y equals 2, and we want to sub it into E, and then that'll be our equivalent 28. Here we talk a lot about diff. I'll talk about that in the next bit. So partial differentiation of expressions. So something that's going to be really important is to know how to differentiate, because differentiation by hand can be really tedious. And so we use the diff command to differentiate expressions. So the way it works is you write diff, and then pretty much whatever expression you want to differentiate, and then with what variable. So if I want to differentiate e, and I want to do it with respect to x, it would be diff ex, and then it gives me the derivative like that. We can also get higher order derivatives by just adding onto here. So if I wanted to, I could just do diff of diff, or just to save time, I could do diff of e with respect to x with respect to x again, and I'll just diff it again. And then just for completeness, if I diff it one last time, we should get 0, and we do. And then obviously that's for x, but we can diff it with whatever variable we'd like. So if we diff it with respect to y, it gives x squared, as expected. But if we try this with f, diff f with respect to x, you'll notice it doesn't work. But that's just because, what is it again, diff only takes in expressions. So we'll worry about differentiating functions in the next slide. But right now for expressions, if you want to differentiate by something repeatedly, and it could get tedious to just write out, differentiate with y, the way to write the shorthand is to differentiate with y, $, and then however many times. So what this reads as is differentiate e with respect to y thrice. So if I do that, it'll give me 0, because if you diff that with respect to y thrice, you get 0. It's also important to recall Clairaut's theorem, which is that you can't always necessarily switch the order in which you differentiate with respect to. And so differentiating with respect to x then y then x should be different to x and y. In this case, because we have a simple expression here, it's not going to make any difference because they're continuous, but that's something to keep in mind. Differentiation of functions. So if we have a function f, we saw that the diff command didn't work. So what we use instead is capital D. So it's capital D, and then square brackets for whatever we want to differentiate with respect to, and then just regular parentheses for what we're differentiating. So if we want to differentiate with respect to x, the way we do that is we look at our mapping and we see that x is the first variable, and so we just differentiate 1. And that just tells it to differentiate with respect to the first variable, and that gives us 2yx minus 1. You'll notice as well that this arrow symbol means that the output is also a function. So meanwhile, the diff command takes in expressions and outputs expressions, the d command takes in functions and outputs functions as well. That'll be really important in a bit. But yeah, we can do the same thing here. If you want to differentiate multiple times, you can just add x again and differentiate with respect to x again. Or if I want to differentiate with respect to y, I'll just add the next variable to be 2, because y is our second input, and so this should just give me 2, and it does. Cool. And then same thing with the $. If you want to do repeated differentiation, you just do whatever variable, $, however many times. Yeah, and so that's exactly what this is. So for higher order derivatives, list more variables inside square brackets, use the $. So the way this can be interpreted is take the derivative of a function f in terms of the first variable thrice and then the second variable twice. Or if you want to expand it out, it's just 1, 1, 1, 2, 2. Cool. And then if you want to evaluate this, since it's a function, we can evaluate functions as we usually do. So for example, say I have this derivative and I want to evaluate it at a certain point. Remember, if we find any function, we'd use this f of and then in brackets 4, 2. In this example, if I want to find 4, 2, you just add it in the brackets after as well, and just subs them in for you 15. And that's because the d command outputs a function. But if we were to do the same here with the diff command, if we were to do that here, it outputs an expression. And so we wouldn't actually be able to do the same trick we did, we just add the 4, 2. Because, yet again, you can't chuck that 4, 2 into an expression. So you'd have to use the subs command again. That's just something to keep in mind. Maxima and minima. So you can also find maxima and minima using Maple. So the way you do that is just with maximize and minimize, quite self-explanatory. Make sure you do a Z instead of an S for your spelling. So if I wanted to maximize the expression that we have, maximize E, we just do maximize E, and it gives me infinity. This example isn't too great because it goes to positive and negative infinity. But just for completeness, if I were to just do min, go to negative infinity as expected. Note as well that you can't maximize and minimize f because f is a function, and what is it? It takes expressions and outputs values as well. And so if we want to add bounds, we just add those with a comma. So we say if I want x between 0 and 1, we just do x equals 0 dot dot 1. And then similarly for y, if I want y between -1 and 1, -1 dot dot 1. And so now it gives me the minimum of E within those bounds. And just like as a little extra, you can add the location command after, and it tells you where to find them. So location. So it says the minimum of E within these bounds is at -2, and it's given in these coordinates, x equals 1, y equals -1. And then similarly for maximize, yeah, does kind of the same. Whoa. Cool. Plotting. Yeah, so you can also use Maple to plot multivariable functions, which could be really useful, especially because multivariable functions can be quite hard to visualize on your own. And the way to do that is just by using plot3d. So if I just do plot3d, and you do plot3d, whatever expression you want, and then whatever ranges you want it to plot from. So if I want to plot this E that I have, I just do plot3d E, and just say I want x is between -1 and 1, y is between -1 and 1 as well. Make sure that's alright. Oh. And it gives me that. Also, you can use your cursor to like drag it around and have a look, which is also quite interesting. So yeah, this could be pretty good for like visualization. And you can also plot multiple expressions on the same set of axes. And the way to do that is to just input it as a set. So if I have a set of expressions, so first expression I'll just have E, and then the next expression I'll have, I don't know, let's see what it has here. X cubed plus y plus 1, x cubed plus y plus 1, short. Now I have a set of expressions, so if I hit enter, it should give me the two curves like that. And I'll leave it as an exercise for the viewer to find out which is which. Cool. Further calculus. I'm just going to clear some space here. And this massive graph. Okay, I guess the graph is staying. Further calculus. The first thing we can do is find partial fractions, and the way we do that is using the convert command. And so the way that looks is just convert, and then whatever expression you want to convert. So in this example, it's 1 over x squared minus 4. And we want to convert it into a partial fraction, and so that's parfrac. And then we want a partial fraction in terms of x, obviously, because we don't want a partial fraction in terms of 4. And that should output a partial fraction as we want it. I'm going to really try and get rid of this. I'm not sure how. Okay. The reason we have to do it in terms of x is because we don't necessarily need fractions of strictly x. This could be a multivariable fraction. So we could have yx squared minus, I don't know, 4y squared. And so if we do respect to x, it gives me the, whoops, missing operator. What is it? It'll give different expressions. Whoops. 4y squared, y, x squared. It'll give different expressions depending on what variable we do. So partial fractions in terms of x and partial fractions in terms of y yield different results. Cool. And then in this example, what they've done is they've converted it to partial fractions, which has allowed integration to be easier. So they've integrated whatever that was with respect to x. Solving differential equations. So in Maple, you can solve differential equations using the dsolve command. And so what we do is we hit dsolve. First, it's actually nicer to define your differential equation before writing out the dsolve command. So in this example, they have y dash plus y equals cos x plus cos. So I'll just write that. So we know that to find y dash, we use the diff command. To be diffing y of x with respect to x. So that's y dash plus y of x equals cos x plus x. Okay, this is really annoying. Beautiful. And so now we've defined an ordinary differential equation, y dash plus y equals cos x plus cos x plus x. And so now if we want to solve it, we can just write dsolve, and then whatever we want it to solve. So in this case, it's just ODE1. And then we want it to find yx. And it gives us the general solution here. You'll see there's an arbitrary constant C1 because the differential equation is a family of curves. And so if you want, you can just plug in the initial conditions and you can get that exactly. But this also isn't limited to just first orders. So we could do ODE2 equals, in this case, we have the double derivative of y. So this would be yx with respect to x twice, minus 3 times the derivative of y with respect to x, plus 2 times y equals 3x squared. So now we've defined our second ODE. We use the same thing, dsolve, and then ODE2 this time, and we still want to find yx, and it can still do that with these arbitrary constants. So yeah, we could find these arbitrary constants by just plugging in manually, but that takes effort and we want to reduce that, and so we can just let Maple do that for us as well. And so the way to do that is to input all of your information as a set of information and then tell it to do so. And so what that looks like is, if I do dsolve and I wanted to find ODE, that's not enough information to give me one particular curve. I need more information, an initial condition. So I include it as a set. So it's a set of information. First, it satisfies the ODE relationship. And then secondly, we also have that y of 0 equals 0. That closes our set. And then now we want to ask it to find yx. It now gives us an exact solution. And then you can do the same thing for derivative initial conditions. So if I hit dsolve, and then do a set of ODE2, and then let's just have y0 equals 0, and then y evaluated at 0 also equals 0 is our set, and we want to find yx. It can do that as well. Cool. Yeah, and so that's just as it said there. Sequences and series. The way to tackle sequences and series is to first try and find a closed form version up to the nth term, and then just take the limit as n goes to infinity. And so in this example, we have, the reciprocal powers of 2. So first we want to find a closed form version of the reciprocal powers of 2. The way we do that is by saying sum, using the sum function, and we're summing the reciprocal powers of 2, 1 over 2 to the k, for k goes between 0 and n. 0 and n. That gives me a closed form version. And now that we have this closed form version, we can take the limit of this as n goes to infinity. So limit of whatever the previous output was, so that's just denoted by percentage sign, as n goes to infinity. And so now we know that the limiting sum of the reciprocal powers of 2, starting at 0, is 2. And you can also do Taylor series. So in order to find a Taylor series in Maple, you use the Taylor command. And it has these 3 inputs that you need. So in this case, it's Taylor series e to the x equals 0 and 5. The way to interpret this is, first it's the function that we're trying to find a Taylor series for, and then it's the x value that we want to find it around, and then it's how many terms you want, because it's not feasible to write out all infinite terms of this Taylor series. And so how many terms are we looking for before the rest you can kind of just group together. So if you just write out that example, we do Taylor of x, and then we want centered around x equals 0, and we want 5 terms. That'll give me that. And if you count, it's 1, 2, 3, 4, 5 terms, and then O of x to the 5 is just all the other terms with power 5 or more. So this gives me the Taylor series, and if I want, I can truncate this down into a polynomial using the convert command from before. And so if I want, I can convert whatever that was beforehand into a polynomial. And so that just truncates it down into a finite polynomial instead of an infinite power series. And that kind of just gets rid of this like little infinite term out here. And then this doesn't necessarily, like, this can happen for any function. So if I wanted to, I could do sine x times e to the x centered at, I don't know, pi, and I only want 4 terms. Then it'll give me the corresponding Taylor series as well. Cool. Further lin alg. This is pretty important. Lin alg houses a lot of the most tedious computations in the course, and so we want to minimize the amount of like human effort, really, because that can just lead to silly mistakes and errors. So first, as a recap, you can define a vector and a matrix as a series of numbers. So the way to do that is, if I have a vector that I want to define, I use the less than symbol, and then whatever inputs we want. So just say 1, 2, 3, 4. And then close it off with a greater than symbol, and then that gives me a column vector. And then for a matrix, let's call A. You can think of it as stacking horizontally a bunch of column vectors. And so the way that would look like is, I don't know, if I want to stack V with something else, I use this vertical line, so V, and then some other vector, let's say 4, 3, 2, 1. And then just to make it a square, I'll add some more, so 5, 6, 7, 8. 8, 7, 6, 5. That's the. So now I have my square matrix. So that's how you make matrices. And then you should already know this, but use the asterisk to multiply by a scalar, just like you do with the real numbers. To add and subtract matrices, you use plus and minus. Note that you have to still stay mathematical, though. You can't just add any matrix with any matrix. They have to be addable, kind of goes without saying. To multiply vectors and matrices, we use a full stop, or the dot. And then you can also raise a matrix to a power, for example, a squared, which is the same as, kind of just multiplying it by itself, and that'll give me that. Cool. And so yeah, here's some examples. If I want to find a dot product, I use this full stop sign. And so if I want to find V dotted with some random thing, I don't know, let's just say itself, use a full stop and it gives you the dot product. This here is really important. This is the linear algebra package. So if I write with linear algebra, it kind of outputs this massive essay. Pretty much all we've done is we've loaded the linear algebra package, so it's pretty much saying all of these new commands we're now free to use. And so with this, we have access to a lot more stuff, and we can be a lot more flexible. So for example, with this new package, I can now define the cross product using the cross product command. Cross product of any two vectors, so V, let's do 1, 2, 3, and then, I don't know, 2, 3, 4. Gives me the cross product. And then the dot product, you can use the dot product command, but we also already have the full stop. And we can also use this package to find a lot of matrix properties that will be really useful. So the dimension of A tells you the dimensions of A. Note that this isn't like the actual vector space dimension, but it's literally just how far across by how far down. So if I were to write dimension A, it's telling us that A is a 4x4 matrix, which we kind of expected. And then row dimension gives us how many rows, so 4. Column dimension gives us how many columns, so also 4. Rank of A gives us the rank. So if rank is 2, then we know it's telling us that it compresses all of R4 into some 2-dimensional subspace. We can also use the basis command. Pretty much what this does is it outputs a set of basis vectors for whatever vectors that we want. So if I were to include 1, 1, 1, 1, 2, 3, and 2, 2, 2. You'll find that 1, 1, 1 and 2, 2, 2 are linearly dependent, and so they're not actually, like, one of them is not actually needed to span whatever these three span. So if you were to write basis, what it outputs is two vectors that can act as a basis for, like, this set. So it's saying these two vectors are linearly independent and they span the same thing as these three vectors, which could be really good for eliminating a lot of the redundancies in a set. Row space, column space, null space. So if I wanted to, I could do row space of a matrix. What this gives me is two row vectors that make up the row space of this. So it's pretty much saying these two row vectors span the same thing as these four rows. Column space, which is a lot more important, gives us two vectors that span the column space. So pretty much this tells us that these two act as kind of a basis for the image. So it's saying these four columns span the same thing as these two columns. So this is just the image. And then the null space gives us the null space. So it's saying these two vectors span the kernel. Cool. Also quite useful is Gaussian elimination and reduced low echelon form. So if I were to do Gaussian elimination of A, it Gaussian eliminates for us, and so now it's reduced A down to row echelon form. If I want it in reduced row echelon form, you just write that. So reduced row echelon form. Did I spell that right? And so now we have A in reduced row echelon form. And then there's also linear solve, which is actually can be really useful. Pretty much linear solve AB. The way to interpret that is we're solving the equation AX equals B. So we're solving the linear equation AX equals B. And here we have an example that'll pretty illustrate quite well what that means. So if I define M to be that matrix there, so 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 10. So just first define the matrix, and we have some vector B equal to 1, 2, 6. Then if we do linear solve, if we define C as linear solve of A, B, pretty much it says C is a, sorry, it's MB. Whoop. Oh yes. So first we need to define M. And if we do linear solve, it's pretty much saying C is a solution to mx equals b. So in theory, mc should equal b. And we can test this with m dot c, and it outputs b, as we expected. And finally, we have eigenvalues and eigenvectors. These can be really tedious to compute by hand, and so doing them by Maple could be really useful. If we want to find the eigenvalues of a matrix, we just use the eigenvalues command. So eigenvalues of A, for example, the way to interpret this is that each component here is an eigenvector. So 0, 0, 18, and -2 are both eigenvectors. And then eigenvalues, eigenvector. Sorry, each of these is an eigenvalue, and then for eigenvectors, it outputs a matrix and a column vector. So the way to interpret this is that each column acts as a basis for the eigenspace corresponding to the eigenvalues in the matrix, in the vector. This is a bit of like a mouthful, so pretty much what it's saying is this first column spans all the eigenvectors of eigenvalue -2. This column spans all the eigenvectors of eigenvalue 18. and then these two vectors both span the eigenspace, so all the eigenvectors of eigenvalue 0. Cool. Now on to 3D geometry.
Sweet. Thanks, Ahmed. Just real quickly, I'm going to see if I can unfreeze the screen. Sweet. Okay, thanks, Ahmed, for covering the first 3 sections. Hi everyone, my name's Chef, and I'll be covering 3D geometry and programming in Maple. So just before we get started, I have a couple tips that I think would be helpful for you guys. So I'll go over those really quickly. In an exam, let's say you have a lot of output coming out, right? And it gets pretty clunky. So if you want to like reset everything, one of the good commands that you can use is called restart. So if you use this, every variable that you had before has been reset. Another thing you can do is if you have way too much stuff cluttering your screen, again, this is very helpful for exams. You just press Control-Alt and just backspace or delete. So now you're dealing with a new blank canvas. Another thing, really quickly, let's say this is like more applicable for if you like need glasses like me. But if the screen is like too small, then you can press Control 1, 2, 3, and like etc. to zoom in, so that it's like more convenient for you. Sweet. I'll cover more tips as we go along, but for now I'll start with 3D geometry, and then I'll look at programming in Maple. So Ahmed already covered the dot and cross product, so what I'll spend more time focusing on is the norm function, and I think the best way to explain what it is through an example. So we'll set up a vector called u, and we'll define it to be 1, 2, 3. Alright, and that's our vector ready. We'll use the norm command. We need 2 parameters for this. The first would be the vector that we want. You could either like store the vector as so, or you could just call it if you've defined it beforehand. I prefer calling it beforehand, like defining it beforehand over here, and then calling it later, so that it doesn't get more cluttered, right? But it's really up to you, it's your preference. So we'll call the first parameter, which is the vector itself, and then the second one is called the p-value. I'm using the p-value of 2 to give you an example of what it does. And then we'll just press enter. Oh, so very important, you need to actually install the linear algebra package. So I'll just really quickly do that. So you need to do with linear algebra. Another helpful tip, so I'll just cross that out. If you press enter, you might have noticed previously that it shows you like all the different packages that has installed, right? If you don't want that cluttering up your screen, what you can do is press the this symbol, and it'll just hide all that output. So it'll take up less space on your screen. So now that we've installed that package, we can try that command again. So the norm function, u and 2, press enter, we get square root of 14. So I'll just very quickly explain what is actually happening. So what the norm command does is it essentially calculates the Euclidean length. I'm sure all of you are familiar with this. So for the case of a p-value of 2, what it's really doing is it's taking the x-coordinate, y-coordinate, and z-coordinate, squaring each of them, summing them up, and square rooting them. So 1 square plus 2 square plus 3 square, that gives you 1 plus 4 plus 9, which is 14. If you just square root, you get square root of 14. Sweet. We'll play around with this function a little bit more. I'll show you guys another thing that you can do with it. So you don't have to always have a p-value of 2. You can try like experimenting with different values. So if I do a p-value of 1, can you guys guess what will happen? Any ideas? I'll give you guys a clue. So when we do 2, what it does, it squares the values, individual values, and then square roots it. So if we use a p-value of 1, essentially it's just going to do power of 1, and then just like take the root of it to the power of 1, which is just like redundant, right? So you're just doing 1 plus 2 plus 3. I'll give you one last example, and I'll show you. If we do if we do a p-value of 3, it's giving us a value of 36 to the power of 1/3. So I'll explain what's happening here. When you use a p-value of 3, what you're really doing is you're doing 1 cube plus 2 cube plus 3 cube. I think that is Yeah, that is 36. And then what you're doing is you're taking the cube root of it. So if you do 36 to the power of 1/3, you get 3.30192. And that is the result that you get. Sweet. So we'll just restart. And we'll move on to a very useful package. This is the Geometry 3D package. With this, you can do a lot of helpful things on your assignments and your exams. So a couple of things that you can do with this is define different objects. This can be anything from points, lines, spheres, triangles, etc. So we have the exhaustive list over here. So yeah, points, lines, planes, spheres, and other objects, such as segments and triangles. So we'll begin with points first, because I think this is a fundamental case, right? If you define a point, you can define a line, and then you can go more complex as you carry on. So we'll look at how to define a point. When we define points, we use the point procedure. It's pretty self-explanatory, but with the point procedure, you need two parameters. Firstly is what you're going to label that point as, and secondly, the exact coordinates of that point. So we'll follow the sample maple output over here, and I'll explain what that does. Sweet. So we've used this command, right? The first parameter, a, is basically the name that I'm storing this point under. So the coordinate of this point, a, is 456, right? So if I press enter, oh, I need to install the package. Okay, you should get the label of what you're storing it as under. Since we're storing it as a, we get the value a. And what you can do is double check that you've stored it correctly. And you can do this by using the detail command. So if you do detail and then enter the name that we stored it in, this will give us the name of the object, the form of the object, and the coordinates of this specific object. In this case, since it's point 3D, this is obviously in reference to the Geometry 3D package, we can see that the coordinates of this point is exactly as we entered it. So this is very it's sort of like a sanity check when you're doing your exams or your assignments. If you want to double check that all your objects that you've defined are what they should be, then you can use the detail command. Sweet, let's move on to defining lines. So there's actually quite a few ways to define lines. On this slide that you see right now, there's 3 ways that we've shown. I'll go through them step by step, but they achieve the same thing, just in different ways. So the first way is we define a line AB by joining 2 different points, A and B. So you're going to be using this point command again. So we already have point A stored in the system, right? So let's define a point B, and we can do some arbitrary coordinates like 1, 2, 3. And we can double check that B has been stored as a point over here. So now that we have 2 points, A and B, we want to make sure that this is joined up and is a line instead. So the way we can do that is pretty self-explanatory. We can use the line command. And here, the first parameter is the name of the line that we want to store it in. So to keep things simple, I'll call this line AB. But again, it's really your choice. You can do whichever line label that you want to do. So we'll call it AB, and then we'll put the 2 different coordinates that we want the line to store. So the first one we'll have is the coordinate of A, which is 456, and the second one will be B, which is 1, 2, 3. Press bracket and then press enter. Now you'll see we've entered a line into the system. We can double check that this is working correctly by doing detail AB. You can ignore this warning for now, it's nothing scary. You can see the name of the object is AB. Form is line 3D now instead of point 3D as you saw over here. And you'll even get an equation of the line in parametric form. Sweet. The second way is you can define a line through a point. So you can use the coordinate system that you entered over here by specifying a certain coordinate, let's say A to be 456. You can make a line by defining it to be going through that point in a certain direction. So I'll show you how that would look. We'll call this line L1. And to enter the second parameter, we just want 2 things. Firstly, which coordinate should it go through? So we'll say it goes through A. And secondly, which direction should it be heading towards? And we can use arbitrary point. So we can just say 1, 1, 1. So if we press enter, we got a new line that is L1. And we can do the detail command again to see if this worked. As you can see, it's stored as a line, and we've even got a parametric equation to show that it's working. The third way is by using this parametric form to define the line. So what we can do is use like a specific parametric value. In this case, we can use t, and I'll show you how that goes. So we'll call this line L2, and for the parametric form, we can define x, y, and z coordinates as so. We'll say x is equals to 1 plus t, y is equals to 2 minus 2 times t, and we can say z is equal to 2 times t. For Maple, even though you clearly define using t, you have to also declare that you are using t as your parametric value. So you have to press comma, and then press t, and press enter. And if we do detail L2, we can check that it's worked. As you can see, we defined it to be 1 plus t for x, 2 minus 2 times t for y, and 2 times t for z. And you can see those match up for the parametric form as well. Sweet. So we'll move on to defining planes, which also, again, it follows from defining points. So similar to lines, you can also define planes in different ways. We've shown 3 ways here, and we'll start with the first way, which is, I guess, the most simplest and most convenient way. So the first way is you just define it as what you want to store the plane as, so we can call it ABC, and the second input is basically the coordinates of the points that you want to be on that plane. So we could just say that we want A and we want B and C to be on that plane. Press enter, and we've got a plane that's ABC. You can double check by using the detail function. Okay, for some reason I'm not able to do detail on the plane, so I'll give you guys another tip of what happens when you encounter something like this. So if you get stuck, let's say during your exam, right, and you're confused, let's say either you can't remember what the command was, or you can't remember like how to call it, what you can do is press question mark and then write up the command. So if we do something like detail, it'll come up with that help page that shows you how it works. To give you an example of what we can do, I can show you an example of normal. So if I do question mark normal, you can see the help function, the help page is shown up, and this side on the left shows every single entry that's similar to the function that we put in. In this case, it's normal, and we can actually check that we're in the right one. We can see we're in the normal calling sequence. And I just remembered the previous command was called norm, so we'll just put norm instead. Okay, to make sure that you're in the right package, remember we were in the linear algebra. Yep. Okay, so previously it was showing us the norm that is in the standard library. So we want the norm that's in linear algebra. So we click over here, and we can see the calling sequence. We can see the parameters that it's usually used. So this is basically like the documentation for this command. What is really helpful for me is scrolling down to see the examples. I think you can really learn like how to use different commands in different ways. So yeah, that's how you can access the command area. I'll show you another way you can do that. So if you forget to do this in your exam, like question mark and then the command, you can also just do it simply like this. There's this help button over here, and then just click Maple Help, and it'll take you to the same system where you can search up different commands. Sweet. All right. Moving on. Okay, yeah. So similar to lines, you can define planes the same way as you want the plane to be stored under one label. In this case, we call it P, and you want to give it a point C that it needs to intersect with and a direction to go along with. And thirdly, you can also use Cartesian coordinates to define your plane. So for example, in this case, we've used x plus y plus z is equal to 7. In fact, I'll call this plane just to show you guys what it looks like. Okay, so as you can see, the form of the object is now plane 3D, but note that even though we described x plus y plus z is equal to 7, the way Maple prefers it is to have the 0 on the right hand side. So it says x plus y plus z minus 7. It doesn't change the output in any way, but it's just good to know. Sweet. Another thing we can define is spheres. So with spheres, you need quite a few different inputs, right? Firstly, as with the previous examples, you need something you want to store the object as, the name for the object. In this case, they've stored it under S. And then you need 4 inputs, which will be 4 points, where essentially these 4 points are inside the sphere, like they're intersecting with the sphere. Currently, we've set up only A and B, so I'll make up 2 coordinates just to show you guys. Point X, and then I'll say this is 7, 8, 9. And I'll call another one called point C, and I'll call this 10, 11, 12. Okay, so let's make the sphere. The first input is going to be what we're going to call it. We will call it S for now. And for the second input, we'll put the different points that we want it to intersect with. So we'll do A, B, X, and C. Oh, let me try again. Okay, so I'm not sure why this wasn't working, but with this case, you can just use 2 different points instead. If you want 2 points to intersect with the sphere, for your second input, you can just put in the 2 points. So in this example, it's A and C. And we can check that this worked by putting detail. As you can see, we get a lot of useful information. If your exam question has something to do with spheres, I think this is like a very useful package to use, Geometry 3D, because you can get so much information handed to you basically. So you can get the radius of the sphere, and by implication, you can also calculate the diameter. You'll get the surface area, volume, and the equation of the sphere. We can also define other objects. So these can be things like segments. So segments like 2 points making a line. I'll quickly show you that. So if we say segment, and we'll call it AB. For the second parameter, we just put in the points AB. AB. So sometimes it might not work because you need the lines to be collinear. So if they're not collinear, obviously you can't make a segment out of it, right? So I'll show you guys if I can work this out. Oh, I see. Small typo here. There should be a comma because you want the 2 different points, right? Okay, now, if we do detail, I'm going to call the name detail AX, you get that it's segment 3D, and you can see the 2 ends of that segment, right? If you wanted like a directed segment instead, so basically you want where it starts and where it ends, all you need to do is just change the command from segment to desegment. So that would just be directed segment. Now we've made a new segment which is directed called AX, and if we do detail of AX, it will show up as a D segment, as you can see. It's pretty similar, but the only difference now is that you've got an initial and end points of this directed segment. Sweet. Another thing you can make is triangle, but because the example is so similar to the other examples, I'm going to skip over it in the interest of time. Sweet, and I'm also going to skip over this as well because it's pretty self-explanatory. You just call the equation. the calling sequence is also very similar. Just the first input is what you want to call it as, and the second thing is the points that you want to use. Sweet. Okay. So this is pretty useful. Intersections. The intersection procedure, you can use it to find the intersection between different objects. So let's say a sphere and a plane, or like a point and a plane, etc., etc. So again, you need two different things. So I guess you need three things. So firstly, you want to like store it as one thing. So let's say we want to store the intersection as a value called g. And then the two other things you need are the two objects that you're intersecting. So let's say a sphere and a line, or like a point and a line. Yep, sweet. Okay. Let's move on to plotting. So Ahmed would have covered this beforehand already, but we'll just show you a bit more examples of the different visualizations you can access. So let's make, I'm going to restart everything. Let's make a point called A with the coordinates 4, 5, 7. And let's make, yeah, don't forget to install the package. Okay, sweet. Now we're going to define the plane with calling it P. We'll have the equation for the plane be x plus y plus z is equal to 7. And we're using the Cartesian coordinates, so we're going to say x, y, z. Sweet. And we're going to define a sphere called S, which will just be A. The second parameter will just be A and 4. Okay. Now if we use the draw function, we can see how this looks. Sweet. Now this is the sphere, and you can play around with it because you also have a triangle over here. You have a triangle over here, but you can see they're not intersecting. I'm using the left click button to drag and view this visualization. I think this is pretty helpful for exams. If you get a question like, oh, at what point do the sphere and plane intersect? Do they intersect? Or if you get a question like, oh, I've got this equation for a sphere, what would this look like? You can put it on Maple and just quickly find the answer. If this is a bit boring, then you can make life more colorful by adding colors. I'll just quickly do that. So color, we'll have the sphere be pink, and we'll have the plane be blue. Ta-da! Okay, so the sphere is now pink and the plane is blue. I'm not sure why this would be useful, but maybe for your assignment, if you want to color things up, you can do that. Sweet. Yeah, so I'm going to quickly gloss over this because of time. There's two other functions that you can use, which is the find angle. And all it is you just enter two parameters. So the first parameter would be a plane, and the second parameter would be the line. And as mentioned before, you can define a line using 2 points, right? So you can, with find angle, you get a radian answer. So your answer will be in radians. Okay, and yeah, the second thing is distance. So for distance, you just need 2 parameters. It can be any objects, so it can be a sphere and a plane and a point, anything. But it needs to make sense, right? If they're touching each other, then the distance is going to be 0. Sweet. So we're moving on to the second section, which is programming in Maple. All right. So with programming in Maple, a lot of ideas that you will have seen in traditional coding languages, you can translate that into Maple, right? Things like loops, conditionals, and procedures. Ahmed has covered a bit of this already, so I'll just show you like the practical things in this section. With these tools, you can evaluate very long expressions, which otherwise would be very tedious to do manually, right? And the other thing to note is that these ideas are built into Maple, so you don't need to install any packages. You don't have to do like with Geometry 3D or with linear algebra, etc. Okay, moving on to procedures. So Ahmed already covered a bit of this. I'll just show you guys the Maple output. Essentially, procedure is just telling Maple like a series of things to do, right? If you say, okay, whatever number you get as your input, just times it by 2, that's your procedure, right? So I'll show you guys an example of this. So we'll call a function x, which takes an input x and multiplies it by 2. And the procedure is 2 times x in the procedure. And then we can call f of 3. Okay, so as you can see, the reason we got 6 is because 3 times 2 is 6, obviously, right? So if we had different calling sequences, if we said f of 8, we would get 16. And that's because it's just following the command from top to bottom. Sweet. Yeah, so the main reason why you want to use it, functions and procedures is because it allows you to do multiple different things, right? For example, if you wanted to double a number, square it, and then add 1, we can just use this procedure over here and set it up maybe at the top of our worksheet, and then just keep calling different values. That way, we don't have to mentally do it each time. The computer just does it for us. Sweet. Okay, moving on to Booleans. So far we've only used Maple as a calculator, right? But you can also use Maple as a truth-seeking device. You can evaluate the truth of mathematical statements. So this can help you find whether truth values of, this can help you find the truth values of complicated expressions, which otherwise will be quite tedious to compute by hand. And this is quite similar to a function that's on many Casio calculators, where you can put into expressions and see if they're true. Like you can say oh, is this expression more than or less than or equal to this? And it will just return true or false. And the same thing will happen over here. So we'll define x to be 6. We'll evaluate b, so that evaluate the Boolean. Is x greater than 3? And we can see this is true because 6 is greater than 3. Now if we called eval b 100x, it's 100 times x minus 99 times x minus 98 times x, and we ask the system, is this greater than 0? Well, I think intuitively you can understand that 100 times any number minus 99 times any number minus 98 times any number would be a negative number. So this returns as false. Sweet. I think this is very helpful for your end of year exams, not so much the lab tests. So the next thing we want to look at is the conditional statements. This is very similar to if-then statements in coding. So sometimes we may want Maple to make the decisions based on the input we give it, right? So the syntax of how to do a conditional statement is, if a certain condition is true, then do this, and they just end the if statement. All right. We've got a little program over here which calculates the circumference of a circle. I'll very quickly write this up. So we've got a program called circumference, which takes a procedure input called r. We do a very quick check if r is less than 0, because the way that the program was set up, we said if radius is negative, we reject it. So, because with distance, you can't have negative distances, right? So we do a little check because the computer reads from top down. So we want to first check if r is less than 0 or not. If r is less than 0, then we say an error, which is that it's a negative value or a negative radius. And we just end the if statement. Okay, and let's say we pick a radius that isn't negative, like a radius of 2. Well, it's not going to pass through this if statement. It's just going to go to the next thing, which is return the evaluated form of 2 times pi times r, which is just the circumference formula. Sweet, and we just end the procedure over here. Okay, and we can see that this is working. So let's call this. Let's say circumference of -2. If we just do this manually as a task, if we have a number that's -2, so if r is -2, the computer would read this line first. If r is less than 0, well, obviously -2 is less than 0, so it's going to go through this if statement, and it's going to get the error negative radius, and that's just going to stop the program there. So if I do this, error in circumference, negative radius. Again, this is purely out of choice. You can say whatever you want to write over here, like negative radius silly, and just call this, you'll see that it shows up in the error message, right? Let's now call a circumference that is valid. So let's say positive 2. When we have positive 2, it's not going to go through this if statement. Instead, it's going to go straight over here and return the correct formula for the circumference, which is 2 pi r. So we should get 2 times 2 times pi, which is 12.566, and that matches up. Sweet. All right, so now onto loops. Loops is very, very important. You have like 2 questions, I think 1 or 2 questions in your lab test that if you have loops, you can do it very, very quickly. Even in your final exam, you're gonna have a couple questions that having the knowledge and competency to do loops is gonna come very, very handy. So I'll explain this and take my time as much as I can while keeping this short. So whenever the main reason you want to use loops is when you have a sequence that you want to sum up, right? Let's say you have a question where you have to sum up like the first 20 natural numbers, or let's say first 200 natural numbers, or you have a certain sequence they want to sum up. Doing that manually is going to take you ages, so that's why you can do this on Maple. So the way it works, the general syntax is we define a starting variable, which we call I, and we define the starting point of where this begins. So in this example, if we want to find the sum of the squares from 2 to 12, so 2 square plus 3 square plus 4 square all the way to 12 square, we can define the start point as 2, and we can define the end point as 12. The other thing you need is the increment value. So every time it does that, by how much does it increase? If I say, usually your examples or like your questions will be 1, but it can change. But in this example, since we want 2 square plus 3 square, you see the difference between the values is 1. We want an increment of 1. And we've initialized a total value at 0. This is very standard procedure for when you have sequences and for loops. So what it does is you initialize it to be 0 in the beginning. When you enter the loop, as you're going through each value, you're updating the value of total, as you can see over here. So total gets updated each time with total plus the I square value. I'll really quickly type this up. Okay, sweet. So as you can see, we've got an output which each time we're printing total and is being updated by the new I square value that is being added. So firstly we had 2 square, which is 4, 2 square plus 3 square, which is 13, and so on and so forth until it reaches the final value. Okay, based on this loop, you can do the next question as well. It's quite similar in syntax and the structure. We've got a practice problem over here. We have a set of prime numbers, 2, 3, 5, 7, and 11, and 13. The question is, how would you evaluate the sum of these primes squared? So this would go 2 square plus 3 square all the way to 11 square plus 13 square. Obviously, we can't use sigma notation because prime numbers don't have a consistent pattern or formula that we can follow yet, right? So the solution is we can use loops instead and do this much quicker than by hand. So we define primes as a class of different objects. In this case, it's just the prime numbers from 2 to 13. Okay, and we initialize, as always, our total to 0, and we set up the loop over here. So for p and primes, you could have said that this is I or p, doesn't matter. For p and primes, do total, and we're just updating the total each time to total plus p square. And then we're just calling the sequence to stop and undo. And if we press enter, we should get the result. Sweet. So if you add up the primes from 2 square all the way to 13 square, you get 377. Alright, let's put this all together. We've got a little system over here which brings and ties in all the ideas from beforehand. So that's things like loops, if statements, so conditionals, and like finding the sum of values, right? Okay, so here's the question. We're going to create a function that takes as input an integer n. and outputs -1 if that integer is negative. So this is very similar to that circumference example where the radius, if negative, would just return an error function. If the integer is negative or 0, then we're going to return -1. But if the integer is positive, what the procedure should do is print the sum of the integers from 1 to n. So let's say if I had, for example, an integer, let's say if I had -2 as n, right? Then the program should return -1 because that number is less than or equal to 0. If I instead have n equals to 3, well, that's valid because it's not a negative number. What it should result is 1 plus 2 plus 3. If I had n equals 10, 1 plus 2 plus etc. all the way to 10. So let's write this up. Okay, we can call this procedure sum, which takes in an input n. And as always, we want to initialize our total to 0. Sorry. And now we want to set up the conditional. So if n is less than 0, then we want to return -1, which is what the brief told us to do. Okay. For numbers where it isn't less than 0, I should add less than or equal to 0 because it says over here, if the integer is negative or 0, it should return -1. If it's not less than or equal to 0, then we do the looping sequence where we do for I from 1 to n, and here is just the classic updating the total. So total plus I, and then we just undo. Sweet. Okay. Shift this onto this message. Oh. Okay, I think okay, I'm not entirely sure what the error is here, but in the sorry. All right. End prop. So end do first and then end prop. Okay. Sign which is protected. Oh, okay. So sometimes what you'll have is values that are protected by Maple system. So I've used this before as well. So sum is a protected value. Another value is d. So we'll just call this summation for now. Okay. So summation 2. And this returns 3 because 1 plus 2 is 3. And I'll show you guys just for checking. If I do a negative number, -2, this will just give us -1. If I do summation of 0, again, this gives us -1. And we can see that this is working. As one last check, we can do summation of 9, which is just 1 plus 2 plus etc. all the way to 9. This should return us 45. Sweet. Okay. All right, that brings us to a close. If you guys haven't signed up, or if you guys haven't done the attendance form, I have the QR code over here. I'll go over that for like a minute if you guys have done that already. Sweet. Okay. All right, and one last thing, we have the cruise coming up. So just the last promo over here. We have the Hollywood Under the Harbor cruise. It's taking place on 18th July, so this Friday. The time is from 7 p.m. and the location is going to be on King Street Wharf. So if you guys are interested, there is the QR code over here as well. Feel free to scan that. But other than that, all done. Sweet.
Can you freeze the screen?
Yeah.